Okay guys, welcome back. So in the last video I concluded by explaining about the basic concepts of thermochemistry. So in this video and the videos hereafter, the series of videos hereafter, I will be talking about the second part of thermochemistry, which are the energy changes and the energy diagrams. So before explaining these concepts, I need to explain you about what is meant by an enthalpy change. So as I mentioned in the first part of my video, enthalpy change is denoted by the symbol delta H, and the enthalpy change for some system is defined as the quantity of heat supplied to a system or given out from a system under the condition of constant pressure, and it's a thermodynamic property. So you know what is meant by a thermodynamic property. I explained to you in my last video about what are the thermodynamic properties and which substances exhibit the thermodynamic properties. So what is important here is that the enthalpy change is a quantity of heat, and the next important thing is that the enthalpy can be supplied to a system or given out from system, and it is measured under constant pressure. So if you meet these requirements, if you meet all these efficiencies, you can tell that the heat change or the quantity of heat supplied or given out from system is the enthalpy change for some system or for some chemical reaction. So the enthalpy change associated with the reaction is given by the difference of the products and the reactants. Now you know that you can calculate the heat given out by the products, right? Heat given out by the products and the heat of the reactants, or the enthalpy of the reactants, or the enthalpy of the products and the enthalpy of the reactants. So we define the enthalpy change for a particular system or a particular reaction, whether it's any type of reaction, whether it's involving of phase changes or whether it's of something you increase the volume or the pressure or some basic quantities, the basic physical quantities. In fact, for any system or for any reaction, chemical reaction, we define the enthalpy change to be the change of the individual enthalpies of the products. This actually the sum of enthalpies of the products. We take it as a whole. We take the sum of the reactants, the enthalpies of the reactants as a whole. So we finally deduct those, and we tell that's equal to the enthalpy change. So enthalpy change, as I mentioned in my last video, if the enthalpy change is negative or delta H is smaller than 0, we call such a reaction or such a system that it undergoes an exothermic reaction, right? Exothermic reaction. And in contrast, when delta H is greater than 0, when the enthalpy change is positive, we call that system or reaction to be endothermic. So exothermic and the endothermic reactions make up different types of enthalpy changes. So then I'll now explain about the different types of enthalpy changes using the equation that we just built up, the delta H equals H products minus H reactants. So some of these reactions that you can define are as follows: the standard enthalpy of formation, the standard enthalpy of combustion, the standard enthalpy of bond dissociation, and the standard enthalpy of neutralization. So you have a number of enthalpies that you can define. So in this video I will be defining only a few of those. So I'll actually break up this presentation into 2 or 3 videos so that it's easy for you to understand about these concepts in detail. So the first 4 enthalpy changes will be discussed in this video. So to begin with, the first enthalpy change that I'll be discussing is the standard enthalpy of formation. So what's special here is that now you know that the enthalpy change is denoted by the symbol delta H. So as I mentioned, there are various types of enthalpy changes. So standard enthalpy of formation is one. So as I mentioned here, there are the standard enthalpy of combustion, standard enthalpy of bond dissociation, standard enthalpy of neutralization. So there are various types of enthalpy changes. All these are enthalpy changes. So delta H is only the enthalpy change for some reaction. Now if you call delta H for the standard enthalpy of formation, and if you use the same symbol in the case of standard enthalpy of combustion, that may cause an error. So what happens here, what we do here is that we define it in another format. So we take the same delta H here, but we take now this 5 symbol or the 0 symbol denotes that it's under standard conditions. So you know what are the standard conditions. I explained to you in my last video. about what are the standard conditions when you are thinking about thermochemistry and the thermochemical changes. So delta H5 or delta H naught in some sources denotes the standard enthalpy. So we put a F here. Because we denote that we actually represent the enthalpy of formation. Now in the case of enthalpy of combustion, we use a C here. So we can easily distinguish now given some data. Now you have different data now. For example, for this reaction you can say that this is actually the formation of water. So hydrogen and half of an oxygen molecule reacts to form water. So the delta HF naught value for that is calculated as minus 286 kilojoules per mole. But if you take another reaction, so the delta HF value will be different from this. Actually, this should be denoted for H2O and that should be denoted for the other substance. Similarly, if you take the standard enthalpy of combustion, this one for water is actually the same value, but what happens is for the other compounds, for most of the other compounds, for the majority of the other compounds, delta HC is not equal to delta HF. So we need some differentiation. So that's the reason as to why we use such a symbol here. So to begin the enthalpy, begin with the enthalpies of formation combustion. First of all, I'll explain what is the standard enthalpy of formation. So now, before explaining about the standard enthalpy of formation, I'll explain about a simple example where you find a standard enthalpy of formation. Now we'll take the same example of the formation of water from one hydrogen molecule and half of an oxygen molecule. So both of these molecules are in the gaseous state, right? And water, you know that its stable condition is when it is in liquid form, not in either in the solid form, which is ice, or in the gaseous form, which is water vapor. So the stable condition is L. So we always denote that the formation of that compound in the stable condition, and the coefficient here, the coefficient of the molecule, or this actually we normally form molecules, but there may be also elements that can be formed, but it's very rare. But in either case, you can see that the coefficient here in the the integer component actually ahead of this compound or the element should be 1. Now if you take you are forming sodium, and you take sodium, some amount of sodium and some amount of chlorine, and you form sodium chloride, so you can say Na plus Cl will form NaCl. Similarly, magnesium and chlorine will form MgCl2. So the coefficient in all these cases is 1. So what is important in the case of standard enthalpy of formation is that now we can also tell that this is equal to 2H2 plus O2 is equal to 2H2O. So that will be minus 286 times 2, which is 572 kilojoules per mole. But in the case of the standard definition, we imply that this coefficient, not this coefficient, the coefficient in which we form the compound in which we form. Now in this case, the compound we form here is H2O, and even in another reaction, the compound that forms in that reaction should have a coefficient, or should have the numerical value ahead of that compound as 1, right? So this the coefficients of the products, right? The coefficients of the products should be arranged accordingly in order to get a coefficient of 1 for the product in which we form in this reaction. So we define the standard enthalpy of formation in such a manner. So we define it as the change that occurs when 1 mole of the compound is formed. So we form 1 mole, so that's the reason as to why we take the coefficient as 1. We form 1 mole, and it should be in the standard state, and it should be from the constituent elements in the standard state. Now you can take now in this case hydrogen and oxygen are always in the gaseous state, but there are cases in which you have some compounds both in the or in many formats. In the case of water, you can say that water is present in all 3 phases. You have water in the solid state, you have water in the liquid state, and you have water in the gaseous state. But we take the constituent elements in the standard state or at the stable state. So the stable state for what is the liquid state. So we have to take the constituent elements. Now H2O cannot be formed from nitrogen and hydrogen. H2O has to be formed from hydrogen and oxygen. And hydrogen and oxygen have to be in their standard state or the stable state. and 1 mole should be formed. So if we form such a reaction, we call that the standard, that is the standard enthalpy of formation for the reaction or for the compound that is formed. So one of the important points is that the standard enthalpy of formation is 0 for elements in their stable state under standard conditions. For example, if you take sodium, you can say that the standard enthalpy of formation for sodium in its solid state is 0, but in the case of the gaseous state of sodium, it's not 0. So now the standard enthalpy of formation for magnesium in its solid state is also 0, but in its gaseous state is not 0. So if you take an element in its stable state or in the standard state, in the state in which you get in the general or the normal environment, you can say that the initial standard enthalpy of formation for such an element is 0. So we can also, as I mentioned in the last video, we can actually draw different energy diagrams for these enthalpy changes. So in a similar way, you can say that the enthalpy of formation of water can be illustrated as follows. So you know that hydrogen and oxygen are in their stable state, so their enthalpy at the beginning is 0. However, when water is formed, you have an enthalpy of minus 286 kilojoules per mole. So as I explained in the last video, you can take these energy levels and you can say that energy is actually given out when water is formed. So this is actually an exothermic reaction. Delta H is minus and delta H means delta H is negative. So when water is formed, energy is given out. So the second type of enthalpy, that enthalpy change I will be talking about in this video, is the standard enthalpy of combustion. So as I mentioned in the standard enthalpy of formation, standard enthalpy of combustion is denoted as delta Hc phi or delta Hc naught. So this differs, the standard enthalpy of combustion differs from the other enthalpies from this symbol. So wherever you get a symbol like this, you can say that this is about the standard enthalpy of combustion for a particular substance. So in a similar way to that of the standard enthalpy of formation, we define the standard enthalpy of combustion so that we actually burn, right? Burn or we combust. Actually, we actually make this a combustion reaction so that the particle or the element or the compound that undergoes this combustion, we actually do complete combustion, not partial combustion. The element or the molecule that undergoes this complete combustion should have a coefficient of 1, or we actually burn only 1 mole. So what we do here is that we actually perform this combustion with the help of oxygen. You know that for combustion you need oxygen. So you take some excess oxygen from some sample and you can make a combustion reaction, and you should take 1 mole and it should be in the stable condition and it should be in the standard state. So we define finally the standard enthalpy of combustion as the enthalpy change. The enthalpy change that occurs when 1 mole of an element or a compound in the standard state undergoes complete combustion in an excess of oxygen. So you take, for example, CH4 or methane or the natural gas, and then you burn it or you undergo with complete combustion. So you form carbon dioxide and 2 molecules of water. So experimental data have shown that delta Hc phi or the standard enthalpy of combustion for CH4 is minus 892 kilojoules per mole. So what's important here is that CH4 should be in the standard state and we should burn one element, actually 1 mole of this element or the compound, and that element should also be burned under the standard state, and it should be completely burned with an excess of oxygen. So as I mentioned, in the case of standard enthalpy of formation, you can also draw energy diagrams for the standard enthalpy of combustion. So the standard enthalpy of combustion for CH4 can be illustrated as follows in an energy diagram. So you know that CH4 gas, the standard enthalpy of CH4 initially is 0 because it's in the standard state, and for O2 also it's 0 because it's in the standard state. So CH4 is the standard enthalpy of CH4 is 0, the standard enthalpy of oxygen is 0, so the standard enthalpy of CH4 and oxygen combined is also 0. So the initial enthalpy of this system is 0. And finally, as I mentioned, we have found that the standard enthalpy of combustion for CH4 is minus 892 kilojoules per mole. So the total enthalpy that is within the products, in fact the products is minus 892 kilojoules per mole. So we again lose heat, and this is an exothermic reaction. So that's it about the standard enthalpy of formation and standard enthalpy of combustion. Now the third enthalpy change that I'll be discussing in this video is the standard enthalpy of bond dissociation. So we denote that by a symbol delta H phi D, right? So what we do here by bond dissociation is that we actually break up bonds. Now if you have hydrogen, we break up. Now you know hydrogen in its standard state occurs as a gas, so it's in the format H2 gas. So we break this bond. So H2 is actually a sigma bond or a single bond. So H bond is broken into two element parts as 2H. Now H we give some heat. We have that HH molecule by a single, that is bonded by a single molecule. It has one electron from the one hydrogen atom, another electron from the other hydrogen atom. It's a single bond or a sigma bond. And what generally happens is that when some energy is given, this bond is actually broken. The energy that is required to break this bond is called the enthalpy of dissociation, and if it is done under standard conditions, it is called the standard enthalpy of bond dissociation. So the standard enthalpy of bond dissociation for some reaction is defined as the enthalpy change that occurs when a gaseous species in the standard state is converted into gaseous components by breaking a mole of bonds. Now in the case of, you can say, carbon dioxide, so it's a gaseous species. So you actually break up those into carbon, oxygen and oxygen. So the bond dissociation enthalpy of carbon dioxide will be some value. And what's important in the case of bond dissociation is that the bond dissociation for any reaction is positive because we give heat. It's actually an endothermic reaction. We give heat, so the bond enthalpy should be positive. Now in the case of some compounds, as in the case of CH4 and some compounds, you can say that you can define one or more bond dissociation energies. For example, CH4, if you take CH4, now when CH4 is broken into its constituents, finally it will be broken into one carbon actually in the gaseous state and 4 hydrogens in the gaseous state. However, you can see that now the median bond energy for such a reaction is, although that is 415 kilojoules per mole, this doesn't happen within a single reaction. It should undergo some 2 or 3 intermediate steps. So the first step of such a reaction is that it breaks away molecules, or actually the elements, individually. Now if you take CH4, you know that 4 hydrogen atoms are bonded to carbon at CH4. So you cannot, first of all, you cannot directly break up all these bonds at once. So if you give some heat, say 415 kilojoules per mole, you may break up. But generally, when you increase the temperature or when you increase the heat given to the system, you break up bonds individually, and then finally you get this final reaction. So in the case of CH4, you have 4 bonds, 4 hydrogen CH bonds. So you break up those bonds individually, so it requires 4 steps. For the first step, CH4 is broken down into CH3 and an H gas. So we have measured that energy to be 426 kilojoules per mole. Similarly, CH3 is broken down into CH2 and H, CH2 is broken down into CH and H, and finally CH is broken down into C and H. So when you add these equations, you finally get that the CH4 is finally broken down into carbon and 4 hydrogens. So because of this difference of energies in these individual steps, what we do here is that we don't take although we add these steps, we don't take the final energy or the total energy needed for such a reaction to be the addition of these energies, what you take is that the total energy or the minimum energy required to dissociate the carbon CH4, the natural gas of the methane into one carbon and 4 hydrogens as the median of these energies. So the energy in the first reaction is 426, the energy in the second reaction is 470, that in the third is 416, and that in the last is 335. So the median bond energy is calculated by adding those and dividing by 4, because it requires 4 steps or 4 parts in this addition. So we get the median bond energy as 415 kilojoules per mole. So bond energy or bond dissociation energy, in fact, is somewhat complex from the concept that you have already learned about the standard enthalpy of formation and standard enthalpy of combustion, because it requires some important points and some complex steps. It requires time to solve, and it involves some complex steps to solve and imagine as to what is going on. So next I'll talk about the factors that affect the bond enthalpy. So because the bond enthalpy, as I mentioned, is one of the complex structures or the complex reactions that you may face when talking or when solving problems on thermochemistry. So some factors affecting this median bond enthalpy is important to learn when studying about the bond enthalpy and the bond dissociation energy or the standard enthalpy of bond dissociation. So actually there are 3 basic factors that affect the median bond enthalpy. One is the bond length, the second one is the number of bonds in an number of bonded electrons, and the final one is the polarity of the bond. Now when the bond length between atoms of a bond decreases, the bond enthalpy and the bond dissociation enthalpy decreases. You know that if you have some bonds, say sodium and chlorine, magnesium and chlorine, when the bond length decreases, the bond enthalpy and the bond enthalpy dissociation energy decreases. When the number of bonded electrons in a bond increases, the bond energy increases. So you know that because when the number of bonded electrons is high, you need more energy. You need more energy to break up these bonds. So because they are bonded now, if you take a single bond compared to double bond, as I have illustrated here, in the case of a double bond you should break up 2 bonds, but in the case of single bond you should only break up 1 bond. So as I mentioned in the example of CH4, you can see that to break up 2 or more bonds you need more energy. So in the case of double bonds, in comparison to the single bond, you can see that more energy is required to break up a double bond, because there are more bonded electrons in a double bond than in a single bond. So the bond energy is varied as the highest bond energy is obtained for compounds which have triple bonds, and the median bond energy is required for compounds that have double bonds, and the least energy is required for elements which have single bonds. The final factor that affects the median bond enthalpy is the polarity of the bond. Now you know that when the electronegativity between 2 atoms of a bond increases, the ionic characteristics of that bond increases. For example, if you take sodium chloride and actually the NaCl bond and the CCl bond, right? So CCl forms carbon tetrachloride, NaCl forms sodium chloride or common salt. So in the case of the NaCl bond in comparison to the CCl bond, you know that the electronegativity difference between Na and Cl is greater than that of the difference of the electronegativities between carbon and chlorine. So you know that CCl bond or carbon tetrachloride, popular solvent, you know that it is a covalent compound, but sodium chloride is an ionic compound. So as I mentioned in the examples or the theories of bonds, you know that when the electronegativity between 2 atoms increases, their ionic characteristics increases. So the bond dissociation enthalpy also increases, because ionic characteristics make this somewhat of a lattice. You know what is a lattice? I explained that in the ionic bonds. So when the polarity of the bond increases, the bond enthalpy dissociation increases. So that's it about the examples or the actually the enthalpy changes that I'll be talking in this video. So in the next video and the videos hereafter, I'll be explaining you with some more, right, with more examples and with more definitions of different enthalpy changes that we can define. So thanks for watching this video and see you soon.